So now we take equilibrium and we talk about precipitates and such. And when we do that, we have a K value that we can actually determine called the KSP, the solubility product equilibrium constant. So where are we coming from on this? Well, here's yeah, okay, there's the beaker with the solution in it. And let's say it's a silver chloride solution. So what I'm saying is that I've dissolved some silver chloride into water, and you know what I noticed? I put some in there, I dissolve, and then all of a sudden, no more of it will dissolve, and the crystals sit on the bottom, and no matter what I do in terms of crunching it up and stuff like that, and my rate of stirring, I'm going to have the same quantity of crystals on the bottom. Well, really what's going on at the microscopic level that we talked about before was that there's going to be particles dissolving to form those ions at the same rate that those ions are coming out to form that solid. And at the microscopic level, that's equilibrium. So we've reached a point where the concentration of the Ag positive and Cl negative is going to be constant over time. If we sprinkled in some more AgCl, it doesn't matter. You can just stir it up. The concentration here in that solution, which is saturated now with AgCl, is not going to change. So we could write that as Ag positive plus Cl negative makes AgCl, and then write an expression for it. But you know what? That leaves us always with the solid chemical on the product side of the reaction, and so the equilibrium expression would be 1 over something. And you know what? That's just messy, and we don't want to do that. So what we do is this. We always take the solid that's on the bottom, the precipitate, or the thing that actually is in solution in a low solubility form now, because it won't dissolve anymore, and we write that chemical first. So it's AgCl solid in equilibrium with. And I know that sounds funny because we're going to write solid here but aqueous ions here. But the deal is that this chemical really is, well, it is aqueous to break down into aqueous ions, but it's a solid that also dissociates in solution to form those ions, so it's totally legit what we're writing. To form Ag positive plus Cl negative, both of these are aqueous. And so, when you write the equilibrium expression for this, you are going to get KSP equals the concentration of, and I'm not going to do it that way, I'm going to write it properly on one line, because the concentration of the Ag positive times the concentration of the Cl negative, those are both aqueous. Sometimes we don't write those a lot. But here's the deal. It's going to be over what? That's a solid, so that's not in the expression, so it's over 1. And so you're always going to get whatever the ions in solution, they are on the right-hand side of the equal sign where the KSP is on the left. And that's how you write the expression for that. Now we can actually have questions where we can determine KSP values from concentrations in solution, but also what are the concentration of ions in solution at points of precipitation? That's actually a very interesting and kind of a powerful chemical type of concept to be able to understand. So that's what we're going to do now with the following questions.